Hey everyone, welcome to the lecture for 2.6. So we're going to be going over centers of mass today. And the way the progression is going to flow is we're first going to start with moments. Then we're going to move on to centers of mass, which we also call centroids. And then we're going to finish with Papu's theorem, Pappus, not sure how to pronounce it, but we're finishing with that. Okay, so as we've been doing so far, we're going to first just consider a discrete set of points, kind of making a representative partition to estimate things. So we're going to talk about the centers of mass of a thin plate. The section starts off with a one-dimensional example. We're just going to bypass that and go straight into R2. So notice that we have an equation for mass represented as an integral, and then we also have equations for moments m sub x and m sub y also represented in an integral. And then our centers of mass, or our centroid, are dependent on these two values. But I want to build up the centers and the mass from a discrete system, and then through a limiting process of a Riemann sum, bring it into the integral form. So to begin with, if we just consider that we have a system of masses here, say we have M1, M2, M3, M4, M5, whatever. So we just have some bodies in space. So each of these points, like, so M1 will be at x1 comma y1, and the mass of that point is given by M1. And then M3 has position x3, y3, and its mass is given by the value of M3. And so x5, x4, 2, y5, y2, y4. So they're just scattered in space. And the total mass of this system is just the sum of the individual masses. So what we have here is that it is the sum from I equals 1 to n. For us, n is 5. We have 5 masses, but in general, you set it up like this, and you just add up the individual masses. And then we have this idea of moments. So moments give you an idea of rotation. Maybe like you can think of it as like where to push from. For now, we'll just consider it by its definition. So m sub x, the moment on the x-axis, is the sum from I equals 1 to n of m sub I, y sub I. Right, so you're just adding up the product of each mass by its height. So it's like you're thinking about the product of the mass itself times the height, the mass itself times the height, the mass itself times the height, et cetera, and so on. And so you're adding up kind of all of these values, and then that will create for you the moment about x. Similarly, you can do the same with y. So m sub y will be defined as I equals 1 to n of mi xi, because here then the distance from the mass to the y-axis, like, so the distance from the y-axis to M3, well, that's x3. The distance from the y-axis to M5 is x5. So that's why you're adding up all of those things. Mm-hmm. So that for us creates our moments for x and y. And then we want to define the center of mass for this system. Again, a discrete system. We're going to go into an infinite system after this, or sorry, a continuous system. So the center of mass, we just define it as x bar, which is the x coordinate for the center of mass, it's just my over m, and y bar is mx over m. So centers of mass are really just, the way I think about them anyway, is if you just kind of like have some blob in space, if I wanted to balance this on a needle, I would first figure out how to separate. I'd get half my area here and half my area here, because if I did that, I could place, like, say, a chopstick along this axis and it should balance perfectly. And so then this would give me x bar. And then similarly, I would do so with the y-axis. I'd get another chopstick perpendicular to this first one. And I would say, okay, I also want, now what I want is half the area here and half the area here. And so then this would be y bar. So this point right here, if I were to have this plate blob perfectly level, I could stick a needle right at this point and it would balance perfectly on that needle, so long as the needle was at x bar comma y bar. That's the idea of center of mass. So now we want to take that into something that's not discrete, something that's continuous. So the idea then is to, instead of kind of looking at this in the plane, we want to upgrade it. So now consider that maybe we have a lamina, which is an infinitely thin plane. And we're just going to look at it from A to B. And so our region is this. This is our plate that I want to balance on a needle. So how do I do that? Well, I'm going to partition it. No surprise there. So if I partition this, the first thing we want to do is say, what's the mass of this partition? So if this is x sub x minus 1, and this is x sub I, sorry, x sub I minus 1 and x sub I, the mass of this mass of this region is going to be the density times the area. So we're going to have that mass equals density times area, and density is still represented by the Greek letter rho. And we're going to assume that rho is constant throughout the region, meaning it's just some number. It doesn't change. And the area, so this is actually just some small sliver, right? So this is rho times that little rectangular area, which we're going to call A sub I. So it represents the area in the ith partition. So the area of this is really straightforward. If this is our function f of x, then what we can do is we can just take a representative height. Like, let's say we take the midpoint, for example. So if I take the midpoint straight through this, then I can estimate this area by saying midpoint, I'm just going to call it xi star instead of having to write this out, but the midpoint is just given by xi minus 1 plus xi over 2, as we did earlier, I think in 2.5. So then this is just f of xi star. So the area A sub I is just given by the width, which is x sub I minus x sub I minus 1 times the height, which is f of x sub I star. So then if I wanted to compute the mass for this entire region, I would just add up all of these things. Notice that's what we did before. We said the mass was just the sum of all the masses. So I'm going to do that. So M, the total mass, is approximately the sum given we have a good partition of all of our masses, so we can go from I equals 1 to n of, oh, I forgot a row. So that was the area, sorry, and then we have to add a row in here. So I should have rho times f of xi star. And I'm not going to write this as xi minus 1. I'm just going to say this is delta x because it's just some change in x. So I'm going to call this delta x. So I get rho f of xi star times delta x, and this is my approximation. If I want it to be exact, I have to use the limiting process. So the limit as n goes to infinity of this Riemann sum this will become the integral. So if we let a be x1 and b equal xn, then this is the integral from a to b of rho f of x dx. Notice we can also write this as rho times integral from a to b of f of x dx. And the integral from a to b of f of x dx is just represents the area under the curve. So this is density times area again. So that's our mass. And we know earlier that centers of mass are a ratio of moments and total mass. So we have total mass. Next, we need to conquer our moments for this region here that's not discrete. So we're going to go ahead and move on to m sub x. So before we saw that this was the sum. This will be an approximation because the partition isn't infinitely fine. So we saw before that this is just 1 to n of mi times xi. But we don't have the mass for this little partition. Oops, sorry, y sub I. But we don't have the mass of this little partition. However, we know the mass in general. We already computed our little mass here. So m sub I is rho times f of xi star times delta x. So stealing that, we get this guy. And then we still have y sub I. So the mind trick here is that you have to treat then each individual rectangle as a point mass. But how do you do that? You have a two-dimensional object that you want to treat it as a point. So the key is to figure out the center of mass for each rectangle. So the center of mass for each rectangle is going to be halfway up and halfway over. So halfway up, this is going to be f of xi star, but I'm only going to go halfway up, so over 2. And then everything else stays the same, so I still have delta x f of xi star, and I still have rho, and I'm still taking the sum from I equals 1 to n. So now if I put this together, I should get the sum from I equals 1 to n rho of, I have 2 f of xi star, so that's going to become squared over 2 delta x. Then if I want to be exact, I use the limiting process. So the limit as n goes to infinity of our summation from I equals 1 to n of rho f of xi star squared over 2 delta x, which becomes then the integral from a to b rho f of x squared. over 2 dx. And we're going to do the same process with m sub y. So give myself some more space. So we know that m sub y should be approximately equal to the sum of the masses times the x coordinate from I equals 1 to n. And we know that each m sub I is given by the area times the density. So height, width times density. Our density is rho. Our height is f of xi star for any partition. And our width is delta x. So now we need to figure out, okay, well, what is x sub I supposed to be? So x sub I, thinking back to the midpoint of this rectangular region here, it should be the halfway point between xi minus 1 and xi. Well, we've already defined that to be xi star. So all I need to do is just to change this. So this is going to become xi star. And just to clean it up a little bit, our summation then is 1 to n rho xi star f of xi star delta x. And as usual, we'll take the limit. So my is equal to the limit as n goes to infinity of this Riemann sum from 1 to n rho xi f xi star, which becomes the integral from a to b rho x f of x dx. So then in order to compute the centroids, that's where all that stuff comes from. So just kind of scrolling back up to the definition briefly, we can see that that's what we ended up with. So m of x is integral a to b rho f of x squared over 2 dx, and my is integral a to b rho x fx dx. And to get the centroid or center of mass, you just divide those by the total mass. So let's do an example of that. Let me scroll all this stuff down. So if we want to find the center of mass of a lamina, which again, this is a infinitely thin plate, and we're going to assume rho is constant, right? So it's just some fixed number. Could be 10, could be 0.1, whatever. So we have a region f of x equaling root x, the x-axis below, Okay, so what we want to do is always graph our region. So this is our region here with f of x equaling the square root of x. So the first thing to do is compute the mass. So the mass is going to be from 0 to 4 rho times our function, which was root x dx. So this should be 2 rho over 3 x to the 3 halves from 0 to 4. So this is 16 rho over 3. So this is our mass. You might be wondering, well, we don't know what rho is, and that's fine, because notice that when we get our centroid, it's going to be our moment over our mass. The moment is going to have rho in it, and our mass is also going to have rho in it. So they'll cancel out, and we'll just end up with some actual number without any unknowns. The next thing we need to do is determine m sub x. So for us, m sub x is going to be the integral from 0 to 4 of rho times our function, root x, squared over 2 dx. So we really get the integral from 0 to 4 of rho halves x dx, which will give us rho fourths x squared on 0 to 4. So this is just 4 rho. So here's another one. So 4 rho, this is m sub x. The next thing we need to compute is m sub y. So this is the other integral from 0 to 4 rho x times f of x dx. So if I simplify the integrand a bit, I'm going to get rho times x to the 3 halves dx, which will leave me with 2 rho over 5 x to the 5 halves from 0 to 4. So that gives me 32, 64 rho over pi. Over 5, not pi, sorry. This is m sub y. So now all that remains is to compute the centroid. So x bar equals m sub y over our mass, my being 64 rho over 5, and our mass being 16 rho over 3. So if we simplify that fraction for x bar, we should get 12/5. And for y bar, we want mx over m, which is 4 rho over 16 rho over 3. And this simplifies to 3/4. So our centroid, so y equals 3/4. Okay, so this is 1. So let's call it there. So our centroid should be, what is that, 2.4? So here's 2, here's 3. 2. So if you were to place a needle under this thing right there, the whole lamina would balance on it. So hopefully you're getting an idea that the area is split top and bottom equally and right and left equally about those two lines. So that's centers of mass for a lamina when we just have one function that's kind of given the region. If we have two functions that are going to determine our region, it's very much the same thing, except that we just need to make the adjustments here and here. So we just need to take the difference of f of x and g of x. So for squaring it, we have to square first, much like the washer method, and then for the other guy here. So those are the only differences.